sense.
Well, actually, you bring up another important point, especially with your mention of epigenetics. Because epigenetics is terribly fashionable within gerontology right now.
Can you explain what epigenetics is?
Epigenetics basically is the study of the changes that happen in cells, whether as a result of aging or as a result of anything else, that cause differences in which genes are turned on and which genes are turned off. So typically these will range from things at the DNA level itself, methylation of cytosines, for example, up through modifications of histones, these proteins that DNA is wrapped around, up through higher level changes to the packing of chromosomes and to chromatin. You know, an awful lot of different things change the behavior with which a cell actually decides which proteins to express and which ones not to. But
let me just interrupt real quick. And for those of you that don't know what express or turn on or off, it just essentially is what he's referring to is that when a gene is turned on or if it's expressed, it's active, it's doing the function it's supposed to do. If the gene is turned off or not expressed, that just means that the gene is there, but it's not doing its function. It's almost as if it's not there.
But here's the thing. When you see a change late in life, you always have to ask yourself, is this change happening as part of aging? Or is it happening as an adaptation to part of aging? Is it happening, in other words, to minimize the pathogenic consequences of some other change? And epigenetic changes in aging are pretty much entirely that latter thing. They're adaptations that are good for us to make the best of a bad job, namely the non-genetic things that are happening elsewhere. We know this simply because they are coordinated. When we look at tissue in bulk, when we look at lots of cells all at the same time, and we ask what's happening in terms of the gene expression changes, what we're seeing is a coordinated response. It's got to be coordinated because otherwise it wouldn't be happening at all this, in the bulk of cells on average. So it's bound to be an adaptation. It's genetically programmed. It's happening because the cells know what their environment is, whether intracellular or extracellular, and they're responding to that environment in the same way that they might respond to an infection or to inflammation or whatever. The only way you can actually ask questions about epigenetics that are meaningful with regard to actual aging rather than adaptations to aging is by looking at individual cells. If you look at individual cells, single cell analysis, then you can quantify the noise, the amount of variation that's happening without any kind of genetic direction. And we're actually doing that. We have had a project for a few years now in the Albert Einstein College of Medicine in New York, looking at precisely this. We're looking specifically at methylation rather than the other aspects of epigenetics. And we're asking, does the amount of epigenetic noise in various tissues increase with age? We're looking in mice. And the hypothesis that we are pursuing is one that I put forward some time ago now, which is essentially that, no, it won't, or at least not to a detectable degree. And the reason it won't is because the quality of DNA maintenance and repair, whether genetic or epigenetic, is driven, in an evolutionary sense, by the need not to die of cancer before you've reproduced. Cancer is by far, in my view, the biggest problem of DNA repair and maintenance because it can kill you with just one cell going seriously wrong in the wrong way. Whereas anything that doesn't have to do with the cell cycle has to affect an awful lot of, a high proportion of the cells in a given tissue before it starts to be pathogenic. And that means a lot of cells.